Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you all to this NPTEL course on traction engineering. Today is lecture 37, where I will try to cover the lateral force developed by an unpowered tractor wheel. In my previous class in lecture 36, where I tried to discuss about the cornering force, where I have given examples related to car tires and truck tires. The reason is we do not have much literature related to cornering force developed by the tractor tires. So, there are very little literature available, and in IIT Kharagpur we have conducted a study how to measure the lateral force developed by an unpowered tractor wheel. So, that I am going to discuss today. So, basically I will try to find out what are the factors which are affecting the lateral force developed by an unpowered wheel. Unpowered wheel means is the tractor front wheel. In a two-wheel drive tractor, the tractor front wheels are unpowered wheels. And then we will try to develop equations how to estimate the coefficient of lateral force, from which we can find out what will be the lateral force developed for a given soil condition. As we know that the lateral force developed when camber angle is 0 depends on slip angle, it depends on normal load, it depends on type of tire. So, the experiments which you conducted, first we tried to develop a setup where you can vary these parameters. Parameter means the slip angles, parameters means the normal load and the inflation pressure. Is because we are talking about contact patch, the lateral force which is developed at the contact patch. So, obviously, is the normal load and the inflation pressure, both are responsible for developing a contact area, developing a contact area. Okay. More the load, lesser the pressure, more will be the contact area. So, likewise. So, the setup which you developed, I have given you different views. In addition to that, I have given you isometric view. There will be a wheel 6/16 8 ply rating wheels, which are normally provided in a two-wheel drive tractor, and there is a provision to vary the slip angle. So, you can see in the figure top view, there is a plate given, okay, where the axle of the wheel can be rotated. If you change the positions, that will give you different slip angles. So, slip angles can be varied from 0 to 40 degree. The one end of the axle which is fitted on which the wheel is fitted is supported on this plate, the other end is supported on a transducer, extended octagonal ring transducer, which is pivoted at one point, so that you can easily rotate the wheel. The axle of the wheel is inserted into this extended octagonal ring transducer. So, there is a bush to which the axle can be inserted, then whatever force, side force is coming, that will be recorded. So, this is the kind of arrangement. I will show a little bit how the forces are recorded. So, when you try to pull the wheel forward, there will be forces acting. So, I have resolved these forces. The side force is P cos alpha plus F S sin alpha, where F sin alpha, where F is nothing but the pulling or the rolling resistance, we can say. So, we are interested about the side force P cos alpha and F sin alpha. So, summation of P cos alpha plus F sin alpha. So, that will be the total side force which is acting on the wheel, and that has to be measured by a Wheatstone bridge, extended octagonal ring transducer, where the Wheatstone bridge Wheatstone bridge principle is used to measure the forces. The axle is inserted in this bush, and one end is mounted on the frame, so that you can easily change the position of the axle. So, thereby you can change the slip angle. Now, once we know the arrangement, then what are the parameters we try to vary. So, this study has been conducted in a sandy clay loam soil, where the properties I have given here are listed here, like what is the coarse sand percentage, fine sand percentage, silt, clay, then what is the ball density, moisture content, cone index value, cohesion, frictional angle. C and phi values are given. So, we try to study the lateral force measurement in a sandy clay loam soil at an cone index value of 456, which is nothing but your medium soil, soft to medium soil, and then at a moisture content of 13%. And the parameters which we varied is normal load, then inflation pressure. Normal load we varied from 1.6 kilonewton to 2.6 kilonewton. Then inflation pressure we varied from 165 kilopascal to 207 kilopascal, and the slip angle which we tried is from 0 degree to 30 degree. 0 degree means the wheel is vertical, we are not changing. 5 degree, in steps of 5 degree we studied, and the parameters we measured are the lateral force, rolling resistance, tire deflection, and tire contact area. Now, when you try to plot the lateral force versus slip angle for these conditions which I just now told, so you can see that lateral force is increasing at a faster rate, then it is slowing down, and thereafter somewhere it is increasing, somewhere it is going down. So, lateral force is a function of slip angle, is a function of normal load. More the load, more will be the lateral force, and the relationship between lateral force and the slip angle is linear up to a certain degree of slip angle. Beyond that, the relationship is irregular. Why it has happened? Because irregularity is because of the accumulation of soil, because the soil on which we tried to test, it is a soft soil. So, virtually the wheel is dragging some amount of soil in the front. Because of that, when there is accumulation of soil, the resistance will increase. So, the lateral force will increase. Okay? So, that is the reason why there is a increase or decrease in the lateral force at a higher slip angle. So, this is the case when the inflation pressure is 165 kilopascal. Now, increase the inflation pressure to 186 kilopascal, and I tried the same experiments. That means, I varied the same variables like normal load and slip angle, and what we observed is the same trend. Up to 10 degree, the lateral force is increasing at a faster rate, they are almost linear. The lateral force and slip angle, they are linearly related. After that, somewhere it is decreasing, somewhere it is increasing. The reason is same. Now, if you compare figure A with figure B, the difference is the lateral force which is developed at an inflation pressure of 165 kilopascal, and the lateral force which is developed at 186 kilopascal, they are not same. The force which is developed with maximum load, you can say 2.6 kilonewton, is roughly around, maximum force is around 2000 Newton, whereas in case of 186 kilopascal, it is around 1700 Newton. The reason is the contact area. Since the lateral force is developed at the contact patch, more the contact area, more will be the lateral force, and lesser the contact area, lesser will be the lateral force developed. The same exercise we tried with 207 kilopascal, and what we observed, same thing, that lateral force is increasing with increase in slip angle up to certain degree, and beyond that there is either it is constant or decreasing or increasing. So, from these three figures, what we can conclude is lateral force is a function of normal load is a function of inflation pressure and slip angle for a given tire and in a given soil condition. That is to be taken. Otherwise, no, it is also dependent on soil condition. So, once you identify, then how to estimate this lateral force? So, what we did is we tried to define a parameter called coefficient of lateral force. What is it? It is the ratio of lateral force to normal load. So, when you try to plot the coefficient of lateral force for 3 different conditions, conditions means 3 different inflation pressure for 3 different normal loads, what we observed here is it is basically an exponential relationship which is fitted for all these 3 conditions, whether it is inflation pressure 165 kilopascal, whether it is an inflation pressure of 186 kilopascal, or whether it is an inflation pressure of 207 kilopascal. In all these cases, the curves are merged into one curve, and that can be expressed by this equation. CLF, which is nothing but the coefficient of lateral force, okay, is equal to A into 1 minus e to the power minus b into alpha, where alpha is the slip angle in degrees. Okay. Now, CLF is dimensionless because lateral force by normal load, it is a dimensionless. So, now it becomes easier for us to estimate the lateral force, because if CLF is related to alpha by a simple equation, if you know alpha, then you can estimate the coefficient of lateral force, provided we know the values of A and B. So, we try to find out now what are the values of A and B. So, these values are listed in this table, which I am going to show now. For different inflation pressures, we try to find out the values of A, B, and the relationship, the equations which we developed, what is its R square, what is the standard error of estimate. So, now what we observed here is with increase in inflation pressure, the coefficients are decreasing, whereas B is increasing in the third digit, we can see 1.174, 0.175, 0.176, and the R square value is very high, and standard of error estimate is also very low. So, that means if you know A value, B value, simply put these values in that equation and then find out what is the coefficient of lateral force. But we then try to develop that instead of calculating individually, if you can relate this A and B with inflation pressure, as we saw that this is varying. So, we try to correlate these values of A with inflation pressure, and what we obtained is they are linearly related to the inflation pressure. A can be written as A is related to the inflation pressure by an equation minus 0.00228 P minus 0.00228 P plus 1.1725. Similarly, B can be related to inflation pressure 10 to the minus 5 P plus 0.1668. That means, if you know the inflation pressure, in this equation the pressure is in kilopascal. So, immediately we will find out, once you know the pressure at which you are going to operate, then the A and B values can be calculated. Then these values can be substituted in that equation as CLF lateral force is equal to A into 1 minus e to the power minus B alpha. And what is the slip angle? If you know, immediately you can calculate what is the value of CLF. Now we know what is the load acting on the wheel. So CLF into load will give you the lateral force which is developed at the contact patch. So in brief, what we have done is we tried to find out what are the parameters which are affecting. Then we try to study how these parameters are influencing the lateral force for a tractor, a front tire which is 6/16 8-ply rating tire, and we tried in a particular soil condition in a soft soil, and then we tried to find out how this lateral force can be estimated. So the equations which we developed, this has to be verified whether it is applicable to the experimental values which are done later, or not on the basis of experimental values which are used for developing the equation. To verify this model, we tried it by conducting some more experiments, and what we observed is very good result. That means R square is nearly 1, and then we can confirm that the equations which is developed, that is exponential relationship which we developed between the coefficient of lateral force and the slip angle, can be utilized for estimating the lateral force developed by a tractor tire. So in brief, the lateral force which is developed by a tractor unpowered wheel is found to be a function of slip angle, it is a function of normal load, it is a function of inflation pressure for any particular soil condition, and we try to study this lateral force by varying these parameters. Then we tried to develop an equation, and we found that an exponential relation is sufficient to estimate the coefficient of lateral force for an unpowered tractor front wheel at a slip angle between 0 to 30 degree. So this indirectly a study which we conducted at IIT Kharagpur, that has been discussed. Since no much literature related to tractor tires are available, that's why I presented it. So this has been taken from one of the papers which I produced in Journal of Terra Mechanics in the year 2014. Thank you.